modern Pelton turbines are mounted on a vertical shaft, and it is kept below the electric generator. So the generator is mounted on the same shaft, and the generator will be above the Pelton wheel. So Pelton wheels, which are mounted on vertical shafts, are driven by jets from several nozzles, and these nozzles will be uniformly spaced around the periphery of the wheel. And obviously, the number of nozzles will be less than the number of buckets. Okay. So both the buckets and the nozzles will be uniformly spaced. So when the Pelton wheel is mounted on a vertical shaft, it is possible to use a large number of jets, up to 6. So for the horizontal shaft Pelton turbine, we have usually 1 or 2 jets. 1 for smaller turbines, 2 for the slightly larger turbines. And these are even larger turbines where you can use 6 jets. But in this case, the shaft must be mounted in such a way that it is vertical. So the jets are produced by needle nozzles. So we'll talk about the nozzles in some detail later on. But here, let me just note that some of the jet speeds may be more than 150 meters per second. That's a pretty large velocity for a liquid jet. Now, in a Pelton turbine installation, the rotor of the electric generator is usually mounted on a horizontal shaft between 2 bearings. And the runner of the Pelton wheel is installed on the projecting end of the shaft. So there are 2 bearings on the shaft, which is horizontal, and in between the 2 bearings you have the electric generator, and you have a projecting end of the shaft, and the runner of the Pelton wheel will be mounted on the projected end of the shaft. So usually you may have 1 Pelton turbine, or there may be 2 Pelton turbines. So this, when you have 1 Pelton turbine on a shaft, it is called a single overhung installation. Now, again, I've highlighted this, written this term in bold. The reason being, you may come across problems in books and exams where they use this term, single overhang installation. So what it means then is that the power that is generated is the same as the power generated by 1 turbine. Now, in bigger installations, runners may be installed on both sides of the generator. And this has an advantage, it equalizes the bearing loads. So you'll have 2 bearings on a shaft, and in between the bearings you'll have the electric generator, and there'll be 2 projecting ends of the shaft on beyond each bearing, and at either end you will have a Pelton turbine. So there'll be 2 Pelton turbines. Okay, so this is referred to as the double overhung installation. So this has a implication that the bearing loads will be equalized. Okay. Now, as far as solving problems is concerned, if you come across this term double overhang installation and you say that the generator generates 10 megawatts of power, it means that each turbine will generate half of 10, that is 5 megawatts. Okay. So when you analyze the problem, you will need to find out what is the power for each turbine. So power for the generator will be double the power of each turbine in the case of a double overhang installation. Usually the 2 turbines will be identical, so each will have the same power. And since they're mounted on the same shaft, they'll be rotating at the same speed. Now the water is supplied to the nozzles from a constant head upstream reservoir. So this upstream reservoir from which the water flows into the nozzle is called head race. And the downstream reservoir into which the water falls is called tail race, that I had mentioned yesterday. Okay. So you should be familiar with these terms, head race and tail race. So usually, these are used in hydroelectric power generation. Okay. So you may have water on top of a hill or mountain at a height, and there may be a shallow slope pressure tunnel, which is a large long pipe which extends from the upstream reservoir or head race to a point which is almost vertically above the location of the turbine. So this is on top of the hill. Okay. And then you will have a specially designed pipe of almost vertical slope, which is called the penstock. This joins the end of the pressure tunnel to the nozzle. So the water in the head race or upstream reservoir will be initially at rest. Okay. So when you open some valves, the water will flow through the shallow pressure tunnel, and then it will go vertically downwards through the penstock. So when the water falls through a large height vertically, the potential energy, the gravitational potential energy of the fluid will be converted to kinetic energy. So at the end of the penstock, the fluid that will come on will have large kinetic energy. Okay. Now there may be some oscillations in the flow rate. So you have what is called a surge tank, which may be installed at the upper end of the penstock. So this may damp out transients in the velocity. Transient means changes in the velocity and pressure with time. So you'll get a steady flow rate. Now there'll be head loss in the penstock. So you may have come across the term head loss in your second year course on fluid mechanics. I'll review that again. But as you know, there are viscous forces acting on the fluid at the pipe wall and in between layers of fluid. Okay. So whenever there is a velocity gradient, layers of fluid will glide over each other, and there is fluid friction or viscous force between layers. And this leads to a loss of useful mechanical energy. Okay, so that energy is actually converted to internal energy of the fluid. That is not useful. So you want to minimize this loss. To minimize the loss, you would like to have penstocks which are large in diameter. Now we would like to predict the power developed by Pelton turbine. As I mentioned yesterday, if you want a very accurate prediction considering viscous forces, etc., then you have to solve the Navier-Stokes equations, and in this case in a rotating frame of reference. And you will need a numerical method to do that. So that falls in the category of what you may call a CFD model or computational fluid dynamics model. Okay. Now in this course, what we'll do is we'll try to make a prediction by making assumptions. Okay, so we'll assume that the fluid will flow behave like an inviscid fluid. So we'll neglect the viscous forces, and this will enable us to get a simple solution. Now, in a second year course, you would have solved many problems using control volumes. Okay, so that is what you will call a global balance. So we consider a system which is a large chunk of fluid inside a control volume. So fluid will enter the control volume and leave the control volume. Okay, and you may predict what are the forces or the torque, etc., on the fluid by applying the laws of conservation of momentum or angular momentum. So for that, you have to evaluate the fluxes crossing the control surface. And usually we make simplifying assumptions. The most common assumption is that you assume the flow to be one-dimensional. So the mass and momentum fluxes crossing control surfaces will be evaluated using one-dimensional approach, and will neglect the viscous forces at the solid walls. Now the implication of using a inviscid model is that the fluid will slip along the solid wall. If you have a viscous fluid which satisfies the continuum hypothesis, then the fluid particles adjacent to solid surfaces will not have any relative tangential velocity component. The fluid will stick to the surface. So if the surface is moving in the tangential direction, then the tangential velocity of the fluid particle at the surface will be equal to the velocity of the surface. That is, the relative velocity will be 0. But the fluid sticks to the solid surface because of viscosity. So if you model it as an inviscid flow, then you have to give up this, what is called the no slip boundary condition, which you might have used when solving the Navier-Stokes equation for duct flows in your second year. Now this is a point which is not emphasized in the books, okay, that we are using an inviscid model. So use of an inviscid model will allow you to predict the direction of the velocity, slip velocity along the surface. So we'll talk about those things in more detail. Now so this is a global approach. If you solve the Navier-Stokes equation, that's a local approach because Navier-Stokes equations represent momentum balance on particles. So there each point is considered to be a particle. Okay. Whereas, so you have a differential equation. In the global approach, you have an integral equation. And here what we'll do is we'll make simplifying assumptions and evaluate some of the integrals. So you can think of three equivalent global approaches. One is using the principle of angular momentum, conservation of angular momentum. Another is using the principle of conservation of energy, that is the first law of thermodynamics. And you can, in this case, you can also get a prediction using the principle of conservation of linear momentum. The reason being that if I take you back to this figure, if the pitch circle radius is very large compared to the height of the bucket, then if you consider the motion of the bucket when it moves from the time when the water jet strikes it till the time when it reaches a point where the water no longer touches it, it is actually moving in an arc of a circle, but that arc may be approximated by a straight line when the radius is very large. Okay, that is usually the case. The wheels are large. Okay. So one may use the principle of balance of linear momentum. Now, I prefer to use the term balance of momentum, balance of energy, and balance of momentum rather than conservation of momentum, conservation of energy, and conservation of angular momentum. I'll explain why. See, when you talk about, say, conservation of mass, if you apply it to a system, then the law of conservation of mass tells you that the mass of the system is unchanged with time. So that means the mass of the system has a value which is independent of time or constant. So some value is conserved. Okay. Now, if you consider a system which always consists of the same fluid particles, so the identity of matter is the same, you can ascribe a linear momentum to it. The conservation of momentum doesn't mean that the momentum doesn't change. The momentum will change if there's an external force on the system. If there's no external force, of course, the value will be unchanged. So when people talk about conservation of momentum, what they mean is that the rate of change of the momentum is equal to the net external force acting on it. So that is basically your Newton's law, second law of motion. Similarly, if you look at angular momentum of the system about some point, okay, or a better term is momentum of momentum. So you have to take the moment of the momentum about a certain point, okay. So that's a separate basic principle. And when you talk about conservation of angular momentum, you don't imply that the angular momentum value is unchanged with time. That will be true. That is, the angular momentum will be unchanged with time only when the net moment or torque acting on the system is zero. But if there is a net torque, then the angular momentum will change. That means the value is changing, nothing is conserved. So when people talk about conservation of angular momentum, what they mean is that the rate at which the angular momentum changes is equal to the net moment acting on the system. Okay. Similarly, again, if you look at total energy, so by total energy, I mean the sum of internal energy of the fluid that is associated with the microscopic motion of the molecules and the bulk kinetic energy of the fluid due to the bulk motion of the particles. So again, that total value may or may not remain the same. So when we talk about conservation of energy, you are actually looking at the rate of change of the total energy due to work interactions and sometimes heat interactions. So prefer to use the term balance rather than conservation. Now, most textbooks on fluid mechanics, any undergraduate textbook on fluid mechanics, I told you before, will have a chapter on hydraulic machines. Okay. And most of the books that are available will use the last principle, the principle of balance of linear momentum, okay, when I'm analyzing the Pelton turbine. Now, when we look at, say, when we analyze the performance of a centrifugal pump, we'll use the first principle which I've stated here, the angular momentum. Now, the two will be equivalent. They should give you the same result. So this, I may talk, if I have time, I'll talk about, because it's interesting to see how the two are equivalent. Okay. Now, the first law of thermodynamics applied to a control volume on an open system, you must have studied in your course on basic thermodynamics. Okay. So you must be familiar with the steady flow energy equation. If you have forgotten, you may want to brush up your knowledge on thermodynamics. At least look at the open system first law, how it is applied to the steady flow of fluid. Now this is also not covered in most books, but we can quickly look at this one and show you that you get the same result as using the third method. All right. Now, as I mentioned here, the reason why you can use the third method, that is the balance of linear momentum, and get the same result as the first method, that is balance of angular momentum, is that H by Rp is much less than 1. So when you see 2 less than sign, it means that this ratio is much less than 1. So it may be typically less than 0.1. Okay. Or certainly more less than 0.2. Okay. Now, if you talk about a dimensional number and say it is small, then you have to say how small is small. You have to quantify it. So you have to say, in this case, H by Rp is a non-dimensional quantity. So you don't have to, it has no units. So if I say H by Rp is much less than 1, what we mean is that H is much less than Rp. So H is the height of the buckets. It is much less than the radius of the wheel or the pitch circle radius. Okay. So if I talk about height being small, then I have to say how small is small. But when I talk about the ratio, I can simply say it's much less than 1. So this is usually the case. In that case, it is permissible to assume, without loss of much accuracy, that the fluid interacts with the rotor at a fixed radial distance, which is the pitch radius of the wheel or the mean radius of flow. So what it means is that if you take moments about the center of the shaft, when finding the angular momentum, you can assume that the moment arm is constant and equal to the pitch circle radius. Okay. So then you are actually taking the linear product, cross product of the linear momentum with a constant radius. So therefore you can guess that the two approaches will be the same if you make this assumption. If you do not make this assumption, then of course the analysis will be more complicated, but the results may not change much. So we can conclude that the performance of the Pelton wheel may be predicted by using linear momentum analysis applied to the fluid inside a translating control volume. So this translating control volume is fixed with respect to a developed or unrolled section of the bucket or blade or vane or whatever you call it. Okay. So we consider an equivalent model where the buckets, instead of undergoing a circular motion in an arc of a circle, is moving in a rectilinear or straight path, and the speed u of the buckets, okay, and in your analysis it will be at control volume, which will be translating, will be the mean speed of the buckets. So if I say capital U is the mean speed, and omega, or capital omega here, is the angular velocity, angular speed of the wheel in radians per second, then the relation between the angular speed and the effective translation speed will be U equal to Rp times omega, where Rp is the radius of the pitch circle, or pitch circle radius. So effectively this is the radius of the wheel, which will be half of the diameter of the wheel. Now in many problems you may be given the angular speed in RPM, that is revolutions per minute. Okay. Then if you want revolutions per second, then you have to divide n by 60. And if you want to convert it to radians per second, then you have this factor of 2 pi. So these are things which you must be very familiar with. Okay. But for the sake of completeness, I have written it down over here and the purpose is to introduce a notation. So omega, the angular speed of the rotation of the wheel or turbine in radians per second will be 2 pi n by 60, where n is the RPM of the wheel. Now usually this omega will be a constant. Of course, when you start a turbine from rest, there will be an angular acceleration and it will start from zero angular speed, but then after a certain period of time has elapsed, it will reach a steady angular speed where omega is a constant. But that steady value will depend on the load. So omega is a parameter which controls the performance of your turbine. So omega may have different constant values in different applications or under different operating conditions. So this U is a parameter in your analysis, or U and omega, they are not independent, they are related. Rp is fixed for a given turbine. Alright, so here I'm showing you one possible control volume for this analysis. Okay. So on the left you have a nozzle which directs a jet of liquid, which is usually water. Okay. And I've shown a coordinate system OX, which is fixed to the nozzle. The nozzle is not moving. So OXYZ is a stationary frame of reference. And this is the converging duct, okay, converging part of the nozzle. So as the fluid flows from left to right through the nozzle, the area, cross-sectional area of flow decreases in the direction of the flow. Now, the volume flow rate across each section must be the same at a given instant of time. Okay. So when the area decreases, the velocity will increase. So this is a prediction of one-dimensional analysis. Now, if you want to do a more sophisticated analysis, you will say the fluid velocity at the surface of the nozzle walls will be zero and there will be a certain velocity profile. In that case, you can interpret the velocity of the one-dimensional approach as being some kind of average velocity, defined as the volume flow rate by the cross-sectional area. So definitely the average velocity of the liquid with constant density will increase as you move from the inlet to the nozzle to the exit to the nozzle. So if you look at the inlet to the converging duct, it will have some velocity, which itself is large because, as I mentioned earlier, the water is falling through a height. So when it's falling through a height, the potential energy of the water is converted to kinetic energy. So the fluid is accelerated further in the nozzle. So here what is happening is the pressure is converted to kinetic energy. So if you model the fluid as an inviscid fluid, when the fluid particle is moving, say, along the center line, the change in potential energy is zero because it's horizontal. Okay. So if the sum of pressure, kinetic energy, and potential energy is the same, if the change in potential energy is negligible inside the nozzle, then the change in pressure is equal to the negative of the change in kinetic energy. Okay. So as the fluid accelerates, the velocity increases. That means the kinetic energy is increasing and the pressure will drop. So there's an energy conversion taking place in the nozzle. That energy conversion is converting pressure to kinetic energy. So the kinetic energy at the jet of the fluid at the jet outlet will be larger than at the nozzle outlet, will be larger than the kinetic energy at the nozzle inlet. So in this figure, I've denoted the jet velocity by capital V with a subscript J. So this J is for the jet. And I've shown this water jet in blue. Okay, so this blue surface is actually a stream surface here. Above you have air, and below also you have air. Okay, so this jet will strike the bucket. So this point is the ridge of the bucket or splitter plate, and that will split the jet into two almost equal halves. Okay, and the fluid will move in a curved path downwards and out like this, and here it will move in a curved path upwards and go out like this. The fluid is turned backwards towards the incoming jet through a large angle. So I've shown the bucket surface here. This is a section through the bucket surface, and this hatches show the solid surface of the blade. Okay. Now this blade will be moving. So I've denoted the x-axis. I've chosen the x-axis such that it is aligned with the direction of the upstream flow. So you can assume that the upstream flow is one-dimensional in the x direction. So the y component of velocity here is 0 at the nozzle outlet. Okay. Now when the jet impinges on the solid, it will exert a force that will cause it to move. Now there will be some friction on the bearings, so effectively there will be a resisting force which will act in the negative x direction. Okay. And if that resisting force is equal to the net force exerted by the air and the liquid on the bucket, then there will be no acceleration. And the bucket or the vane or the blade, whatever you call it, will move with a constant speed, which I am denoting by capital U. Okay. So since the bucket is moving, if you do a control volume analysis, then you have to use a moving control volume analysis. So I've shown the control volume using dotted lines. Okay. So I have looked at the surface and I have labeled this first surface as 1. So this, as you can see, is an inlet because the fluid will or liquid will enter the control volume through this surface. Okay. And there are two outlets. I have labeled one of them as 2. So here the fluid will flow perpendicular to this cross-sectional area over here. So this is an outlet because the fluid will move out. And 3 is also another outlet where the fluid will move upwards. In 2, across the section 2, the fluid will move downwards. Across the section 3, the fluid will move upwards. And across section 1, it will enter the control volume horizontally. Okay. Now here I have shown you a coordinate system which I have called O prime, X prime, Y prime. So O prime is the origin of this moving coordinate system. So in this figure, the way I have drawn it, the axis O prime, X prime is parallel to the axis OX. And the axis O prime, Y prime is parallel to the axis OY. And if the blade is translating in the X direction, then at all instants of time, these axes will remain parallel. So there will be no rotation here. So that is the approximation that we are using. Okay. So this O prime, X prime, Y prime then is a translating frame of reference. Now I've shown you the forces due to pressure acting on the system inside the control volume. So as you can see, I have taken a control volume which you usually see in books, which includes part of the solid surface. So it's not just the fluid. You could also have taken a control volume which is just the fluid, but then you have to separately draw a free body diagram of the solid vane. And you have to take into account the fact that the net force exerted by the impinging liquid on the solid vane is equal and opposite to the net force exerted by the wane on the fluid. Okay. But you can think of it this way: the solid is also a continuum, although there is no deformation of the particles. Okay. And you can apply Reynolds transport theorem to the solid part also. And in this case, the control volume includes the solid as well as the liquid. So this actually simplifies the analysis, because then you have to just find the forces exerted by the surrounding liquid and air on the fluid which is inside the control volume at time t. Okay. Of course, here inside the control volume you have not only the fluid but also the solid. Okay. So all the material within these dotted lines is the system at time t. Okay. Now, if you look at the figure at the bottom, okay, so I've written here air above below to show you that this is there is a free surface or interface between the liquid and the liquid jet and the air. And on this side of the bucket also you have air. So you can say the pressure exerted by the air on the outer surface of the bucket or vane is a distributed force with a value which will be the atmospheric pressure. And as you know, this is a compressive force, it will always act in the normal direction. So if you see the arrows that which we have done, they are normal to the surface. Now, if you look at this surface, that is the stream surface, that which is the interface between the air and the liquid jet. On this side also you have air, so the distributed force due to the atmospheric pressure will also be constant here. It's a uniform pressure. Okay, this figure is not to scale. Okay, but I've written the value P subscript A to tell you that that is atmospheric pressure. The subscript A is for atmospheric pressure. Okay. Now, if you look at section 2 and section 3, that is this or this. Okay. So there are points on this section where you have fluid particles, not particles of air. Okay. So what will be the pressure there? Well, it may be different from atmospheric pressure, but consider the fact that the diameter of the jet is small. Okay. And if you look at the jet over here at section 1, it may be a circular jet, but all along the circle, the periphery of the jet, the pressure is atmospheric pressure. So it's a good approximation to say that the pressure at all points inside the liquid jet is roughly atmospheric pressure. So in that case, the fluid particles will actually undergo a free fall. Okay, so the jet will not be exactly horizontal, it will bend slightly downwards. Okay, but since the velocity of the jet is very large, we can neglect that downward deflection of the jet. So for simplicity, we are not considering the deflection of the jet over here. We are assuming that fluid or liquid exiting from the jet is moving horizontally. Actually, it will move in a slightly parabolic arc. So the same thing is true of sections 2 and 3. So here I've shown the distributed force due to pressure on section 2 and section 3 as being atmospheric pressure. So at all points on the control surface, then the force is a distributed load which has a constant value, which is atmospheric pressure. Now, can you tell me what will be the net force on the system due to the pressure? If you have a body, closed body,
Zero,
and you have
zero.
atmospheric pressure
Zero,
acting
zero,
all
zero,
around
zero.
the body,
Zero.
the resultant will be 0. So that's a big simplification. Okay. Now this is true intuitive. You can tell it intuitively, but in the first class I promised to develop the subject logically from first principles. So I'll do some analysis and show you why the net force on a complex closed surface will be 0. That will require use of the divergence theorem. But anyway, I cannot talk about all the details in one class. Okay, so I'll go bit by bit, and then I may come back to these figures and explain to you some more finer points about it. So on this figure, of course, I have not shown the external force, which will keep it from accelerating. Okay. So here you see the net force due to pressure is 0. Okay, net resultant force. Now here there will be some, if you look at section 2 and section 3, okay, you may have some viscous forces here, but those we are neglecting. So we are making an assumption which may not be stated in all the books, that the fluid is inviscid. If you assume that fluid to be, if you consider the effects of viscosity, then the analysis becomes too complicated. You cannot make predictions. Okay. So in order to make predictions, which may or may not be exactly 100% accurate, you have to make simplifying assumptions. Okay. Now, of course, here you see that if you look at this streamline, the fluid is turning in a circular arc. Okay. Now I can consider a central streamline which I have not drawn in this figure. Unfortunately, I don't have access to a blackboard, so I cannot draw it. So in the next class, hopefully, I'll be able to scan another figure. So, but I can show it using the cursors. Consider a central streamline. It will go like this. It will bend and go like this. All right. So when a fluid is moving in a curvilinear path, there will be a radial pressure gradient, because the net force due to pressure will be balanced by the centrifugal force on the particle. Okay. So the pressure when the fluid is moving in a bend will be higher on the outer side of the bend. Okay. So if we go along this path, for example, here, at this point, the pressure is atmospheric pressure, but if you go downwards, the pressure will be more than atmospheric pressure. So if you just look at the free body diagram of the vein, on the outside of the vein, you have atmospheric pressure, but on the inside of the vein, which is wetted by the liquid, the pressure will be more than atmospheric pressure. So there will be a net force on the vein. Okay. But we are not considering the vein separately. For simplicity, I am taking a control volume which includes the vein as well as the liquid. In that case, what happens, that advantage of this using this control volume is that at all points on the control surface, the pressure is constant and has the same value, so net value is 0. But there's a change in the momentum, so there will be a force exerted on the thing. And there must be an external force, otherwise this will start to accelerate. Okay. So now I'll be sending this to you later on. There may be some minor typing errors which I'll correct, and I'll mail this when it's 100% correct to you. Okay. So you can go through it again, and I have written down things in case you have not listened to my lecture. Okay, you'll be able to figure out. So section 1 of the control volume is an inlet section. I've already mentioned this, and 2 and 3 are outlets. So to do the analysis, we'll make assumptions. The first assumption that we're making is that the bucket height is small compared to the radius of the disk. If this were not the case, then we cannot approximate the motion of the bucket by a rectilinear motion, that is movement in a straight line. It actually moves in an arc of a circle, but we are neglecting the curvature of that arc. Now we have assumed the fluid will behave like an inviscid fluid, so we'll call it an inviscid flow. That is, we are going to assume that the viscous forces are negligible. Actually, there will be some viscous forces, but if they have a small effect, then the prediction will be okay. Now, if you look at any book on fluid mechanics, you'll see the same this assumption. When you have a moving, translating control volume, they'll assume that the flow is steady in a frame of reference, translating with velocity. It does not come here. I don't know why. Velocity, I meant u. So you see, there's some problem with the document here. The u has not come. Okay. Now, what does this mean? That is, what is the difference between a flow being steady in a stationary frame and a translating frame? So if you go back here, there are two reference frames. This is, so the flow might be stationary, steady in the stationary frame, or it might be stationary in the translating frame. If you are lucky, it might be steady in both. but it may or may not occur. Okay. So these things unfortunately are not discussed in any undergraduate book on fluid mechanics that I've come across. Okay. But since in IIT we teach engineering as a science, I'll spend quite a bit of time in explaining these things to you. Okay. So this chapter on fluid machinery you'll find in any book, but not in great depth. Okay. And courses on fluid machinery or hydraulic machines will be taught in all engineering colleges. Okay. But my philosophy is that you are studying in IIT, so you should learn something more than the students in other colleges. Okay. So we'll use what is called a Galilean transformation to explain to you what is the difference between a flow being steady in a translating frame of reference and a flow being steady in a stationary frame of reference. So I've written a question here. What does this mean? So I'll clarify this later. Okay. If I try to explain everything today, then you'll get lost. So today I'm just mentioning the assumption that you're making. Okay. Now another assumption that you're making is the pressure inside the liquid at section 1, 2, and 3 is atmospheric pressure. Now I've given you the justification for that. At sections 1, 2, and 3, you have a streamlines which are almost straight lines when they're coming out. Okay. So you can neglect the centrifugal effect over here. Okay. Unlike somewhere here where the curvature is large. Okay. And all around the jet, the pressure is atmospheric pressure, and the cross-sectional area or the diameter of the jet is very small. Okay. So the variation of pressure inside, there may be some variation in practice, but it is very small. So it's a good approximation to say that when a liquid jet comes out into the atmosphere and it's not moving in a path with large curvature, then you will have everywhere the pressure equal to the atmospheric pressure. But that may not be true if we take a section like here. Across this section, the pressure will vary from atmospheric pressure to a value larger than the pressure. But if you look at the cross section here, if you move from this point to this point across section 1, okay, or if you move from this point to this point across section 2, or you move from section this point to this point across section 3. Here, if I draw the streamlines, there will be almost be straight lines parallel to this surface here. Okay, so there it's a good approximation to say that the pressure is atmospheric pressure. Now, another assumption that you will see. So, I believe we have used Fox, McDonald, and Pritchard as the reference text in your second year course. Now, the book has good problems, but it's not very sound on this sound in explaining theoretical assumptions. You see this assumption that I've written over here. They'll say you assume that there's no change in the speed of the water jet relative to the bucket as it moves or slips along the surface of the blade or vane. What is the justification for this? Okay. So, well, first of all, we have assumed the fluid to be an inviscid fluid. So, inviscid fluid can slip along the wall. Okay. Now, if the stationary surface is solid surface is stationary, then under certain conditions, the slip velocity of the fluid along the surface may be constant. But here, when the surface is moving, it is not the velocity of the fluid particle, not the absolute velocity, but the relative velocity of the particle that remains unchanged. Okay. Now, again, this has something to do with point number 3, and this is not explained in any book that I have come across. So I'll need to spend a bit of time since you will not find these concepts in other books. Okay. And if you have any queries, you can ask me later on. Okay. So I'll give you a rigorous justification for assumption number 5. But before that, I will have to explain to you exactly what this means. Okay. The number 3. Okay. Now I'll stop sharing this and open another document. So are you able to see the second document?
No, sir.
No, sir. No, sir.
You are able to see?
No, sir.
So I think you need to present once again. Present from the start, like afresh.
Okay. Yeah. All right. Now is it visible?
Yes, sir.
Yes,
Yes.
sir.
Okay. So today I'll not talk in detail about the Galilean transformation. Okay. But I'll just give you an overview. Okay. I'll explain the mathematics later on. Okay. Now, if you look at a book on relativity, you will come across the Lorentz transformation. You might have read it in your physics courses. Okay. So here we'll be talking about Galilean transformation named after Galileo. Okay. So here this figure shows you two frames of reference. The left one, OXY, is the stationary reference frame, and the right one, O prime, X prime, Y prime, is the frame of reference which is translating. Okay. Now, I've already shown you the buckets, and I've shown you the two-dimensional view of the frame OXY and O prime, X prime, Y prime. Okay, here I'm showing you the details. So the red one, this frame of reference will be moving to the right, parallel to the axis OX. Okay. So for simplicity here, I'm assuming that at time t equal to 0, the two frames are coincident. So the origin O of the fixed reference frame and the origin O prime of the moving reference frame coincide at time t. So as t increases, the distance between them will increase. So O prime will move to the right. And the distance between the axis OY and OY prime then will be ut. Okay. Now suppose you have a case where initially they are not coincident, but they're parallel. Then you simply add to this ut some initial value, ut plus x initial, let us say, where x initial is the initial distance between O and O prime. Okay. And we're considering a case where this capital U is constant. Otherwise, you have to integrate. If U is a function of time, to find the distance, then you have to integrate ut dt. So if U is constant, then this distance is simply ut. So let OXYZ be a stationary frame of reference and O prime, X prime, Y prime be a translating frame, such that the axes are always parallel. And the reference UX, so I've used E subscript X for the unit vector in the X direction. Many books might use I, but later on we'll use cylindrical coordinates, where we'll use ER, EV, EZ. So here I've simply called it EX. So we are considering a case where it's moving with a constant velocity. Excuse me. The origins O prime and O are coincident at time t equal to 0. And these axes are also coincident. Okay. Now, let me ask you a question. Is this translating frame an inertial frame?
Yes, sir. Because it's not accelerating, right?
Right. Because we are saying that it is the speed is constant and the direction of motion is also constant. So the velocity of the origin O prime is unchanged with time, it's a constant, so therefore it's not a non-accelerating frame. So therefore then you can apply Newton's law using the velocities related to the moving frame. Had this frame been accelerating, then there would have been an additional equation in the equations of motion which involved the acceleration of the origin. Okay. So in some problems you have to do that also, but here you don't have to do that. Now, the coordinate transformation, here we have chosen the axis such that if you have a point somewhere here, the y coordinates in the two reference frames and the z coordinates are the same, but the x coordinates differ because the origins O and O prime are different. And the difference between x prime and x, the coordinates, x coordinate measured in the right frame and the left frame differ by ut. Okay. So I'll talk about it in more detail later on. For the timing, I simply say that x prime is x minus ut, and here I have generalized it and said minus x initial. But in the figure, for simplicity, I have used x initial equal to 0. Okay. Now, since the flow quantities depend on x, y, z, and t, to find the partial derivatives, you have to use the chain rule. Okay. So what I've done is I've introduced a notation t prime equal to t. Okay. So we'll be considering a transformation from x prime, y prime, z prime, and t prime to x, y, z, and t. So this is a coordinate transformation. So in equations 1, a, b, c, and d, on the left hand side, you have the prime quantities. On the right hand side, you have the original quantities, x, y, z, t. Okay. And there's a parameter in the transformation which is capital U. If you come into the derivatives, partial derivatives. Now I can move this term to the right hand side and say x is x prime plus ut plus x. Okay. Now, of course, here I forgot to put the prime here. I wanted to have the original transformation coordinates x, y, z, and the time t on the left hand side, and the prime variables on the right hand side. So if you say this is a 1 a b c d is the forward transformation, then 2 a b c d is the inverse transformation. Okay. Now, while the equation 2a is correct, it's not what I wanted, so I missed the prime here. So I'll correct it before I present it next time. Okay, so I wanted on the right hand side of equations 2 all the prime quantities. All right. Now, using this transformation, we can find relations between partial derivatives with respect to x, y, z, and t, and partial derivatives with respect to x prime, y prime, z prime, and t prime. And those, then you can transform your Navier-Stokes equation or your Euler's equations for inviscid flow. Okay. And this will also help you to find the form of Reynolds transport theorem in a translating control volume that is amenable to analysis. Okay. So you may have solved some problems using translating control volumes in your second year, but perhaps you have just made some assumptions and just got the result without understanding how it has come about. So since this is a fourth year level course, I'm going to spend some time explaining these things to you in detail. Okay. So today I've just introduced the Galilean transformation. I'll not talk about the mathematical details today. Okay. Now, my feeling is that if I don't include this, then this course will not look like an advanced course. Okay. And you may not find it interesting. So I hope that you will spend some time in understanding the mathematics, which I'll be talking about later on. So I'll close this document again and open another document. Do you want a short break?
Yes, sir.
Okay, I think if I keep talking for 2 hours at a stretch, it will be too tiring. Okay. And here in Kharagpur, there is a thunderstorm. So I would like to stop for about, say, 10 minutes.
Okay.
So after 10 minutes, I'll start again. Huh? Is it? Okay. So for the timing, I'll hang up. So you can join back in another 10 minutes or maybe 15 minutes, let us say. It is 5 past 5 now. So at 5:20, we can start.